Hey, Yuga beings. I hope you're enjoying DSS 2021 so far and all the awesome speakers who have presented. Super excited to have you here for my talk over geo-distribution for resilience, performance, and compliance. Before starting, a little bit about me. I've been working at Yugabyte for just over a year, and I'm currently leading the sales engineering team for our new cloud product. Before that, I worked on this enterprise sales engineering team where I helped Fortune 500 companies install, migrate, and adopt Yugabyte. Before working at Yugabyte, I worked at DataStax, which deployed enterprise-grade Cassandra for companies across the globe. And as you can see at the little picture at the bottom there, I'm a proud CU Buff alumni. So what is a distributed database? In layman's term, it's a single database that is spread across two or more geographically distinct locations and runs without experienced performance delays in executing transactions. So let's dissect this a little bit when we talk about being across multiple regions. That can mean multiple data centers, distinct regions like an AWS and GCP, which can be across multiple countries or continents. And the other way we can talk about different regions is when we talk about multiple clouds. So for instance, if you want to deploy across both AWS, GCP, and Azure, all within the same database. And you may be asking yourself, well, now they're just selling me magic beans. There's no way you can get around the age-old problem of physics. And in the past, that was true. But with Yugabyte, we actually give you several different options of how to get around this physics problem. Before I get to how we work around this issue, first I want to explain exactly what I mean by the physics problem. What we're really trying to solve here is the networking latencies when we communicate across the wire. If you see in this picture below, the US West Coast there is a latency for traffic that needs to travel across the United States of about 60 milliseconds. And when we try to send data somewhere else like Australia, those latencies can triple to 150 milliseconds or more. And in the world we live in, those kind of latencies are just not tolerable for your end users. So what we're really trying to do is get your data as close as you can to your users. And that way they have the best experience possible. So why deploy geo-distributed databases? Now, there could be a variety of reasons why someone may want to deploy a distributed database. It could be that they want resilience across their clusters, so that if there were to lose a local region or data center, the application can continue to run without any downtime. Or it could be that you want to be able to deploy a database and keep the data local to their customer in order to have those low latencies and high performance. The other big reason someone would want to have just a geo-distributed database if there's specific requirements like GDPR that require data to reside local to the customer or local within a country. So how exactly does Yugabyte solve this issue? Well, first, it's important to understand from a high level how Yugabyte is deployed. Yugabyte is deployed across nodes that then make up a cluster. So for instance, in this case, we may have an application that is then connected to a Yugabyte cluster that has 3 nodes in it. One key concept in Yugabyte is the idea of sharding. At a high level, sharding is where you take a table and break it up in pieces or shards. Then with Yugabyte, we evenly distribute those tablets across the nodes within the cluster, as you can see here. Now, all of this is 100% transparent to the user and is done automatically, so you as the user never have to worry about setting this up. So how we design this database is kind of right what you see here. On the left, we have the high-level overview of how Yugabyte is built. On the top, we have a pluggable query layer where you can see 2 different APIs. The first is our YSQL API, which is feature-compatible Postgres API. What we decided was that instead of recreating the wheel here, let's take a well-known database technology and rip the top half of its query layer and integrate that with Yugabyte. What this allows is for an easy transition for someone familiar with Postgres and makes migrating to Yugabyte that much easier. The second API we offer is a YSQL API, which is a Cassandra-compatible API. Anyone who used Cassandra in the past, like me, would feel right at home using this API. Now, both of these APIs are built on top of a distributed data store that uses a custom ROX DB engine as its foundation. Here's where we take care of all the sharding, replication, and management of distributed transactions. Now, on the right, you see 2 common DB technologies, Aurora and Google Spanner. Aurora has been one of the fastest growing products for AWS in the past years and has direct compatibility with Postgres. The main issue when compared to Yugabyte is scale. There's just no way to horizontally scale writes with Aurora, which can lead users to run into a vertical scale wall where there's just no way around it. On the other hand, Google Spanner does a great job of scaling around the vertical scale wall for writes and reads, but the main drawback is it lacks a number of the RDBMS features that many of its users need when compared to Yugabyte Aurora. This makes adoption more difficult and may cause users to have to redesign their app. The last database I'd like to quickly compare is more on the NoSQL side, which is Cassandra. Cassandra does a fantastic job at horizontally scaling and has a built-in HA when nodes or DCs fail, similar to Yugabyte. However, the one place it does have issues is with consistency. If your app would need to have ACID compliance, Cassandra just couldn't help you out there, and is actually designed to be eventually consistent. What we have done with Yugabyte is take the learnings from these different databases and mold it into a new database that allows for fantastic scale while keeping ACID compliance, but then also bring in those familiar RDBMS features to make it easier for users to adopt. By default, Yugabyte is deployed in what we call a synchronous architecture. In this setup, we have the idea of a replication factor, which is how many copies of data live within a cluster. What we generally recommend is to have a replication factor 3 for most production systems. Once the data is copied, what those copies do is create a raft group, and then one of those copies is elected the leader of that data. When a write comes in for that piece of data, it has to go to the tablet leader, and then get acknowledgement from one of the other copies depending on your RF. And then after that, the write will succeed. Then for reads, the query will go straight to the tablet leader and does not need an acknowledgement from any of the other copies. The way we handle these writes and reads is the reason why we're able to have such high consistency, and the fact that the tablet leader is always involved in both the write and the read. With this setup, this also gives you the fault tolerance that if you were to lose a node, there would be no impact on your application. Since you have multiple copies of the data spread across different nodes, you never have to worry about it if a single node or sometimes a single AZ goes down. There is no impact. But one of the downsides of this configuration is that while you have the resilience and consistency, there could be higher latencies due to that networking issue we talked about. Here are some of the common deployment strategies we see with synchronous replication. In the first deployment, we would have this high resilience across AZs, high consistency because of how Yugabyte handles query natively, and the low latencies since it's all within the same region. Now, the second most common is where we have a single cluster that spans across multiple regions. So this could be US West, US East, and maybe somewhere in Europe. The great part about this configuration is you still have that high resilience and the high consistency, but this is where you start to see those latencies start to become an issue since you have to go across the wire to grab that for those writes. The last common deployment strategy, if you want to deploy across multiple clouds within the same cluster. In the new cloud native world, you don't want to be tied to a single cloud vendor. You want to be able to mix and match and be able to change on a whim. Yugabyte gives you that flexibility to be deployed across multiple cloud providers and even on-premise data centers. One customer who is currently using synchronous architecture is a top 5 global retailer that operates stores across the world. Currently, what they use Yugabyte for is their source of record for their product catalog. The catalog has hundreds of millions of items that need to be queried hundreds of thousands of times per second. They also need to be able to handle the scale during those peak traffic times like Cyber Monday, Black Friday, and during COVID. COVID caused a massive spike in online sales, with many retailers saying it was basically Black Friday every Friday. While their previous solution, Cassandra, allowed for scaling, one of the major issues for them was consistency. What Yugabyte gave them in the synchronous architecture is the ability to have ACID level consistency, which ended up saving them millions of dollars in lost revenue per year. Here's how that customer actually is currently deploying their cluster. It's set up within 3 regions and 9 nodes in each, one in the US East, West, and South. Now, as many of you know, last year there was the major snowstorm that hit Texas that caused power outages across the state. This actually led to the entire US South data center to go down. And even though this outage caused major issues across the United States, because of the built-in high availability of Yugabyte, in the multi-region setup, they suffered 0 downtime and remained available during the entirety of the Texas power outage. Once the data center was recovered, the cluster automatically repaired itself and resynced the data to that data center. While many distributed environments, this can take multiple hours or even days to resync the data, with Yugabyte, it takes minutes to a couple of hours, depending on the data density. What I've actually seen in the past with something like Cassandra is it can take 8 days to resync what would only take 7 hours for Yugabyte. The next option for getting around this physics problem is what we call follow reads. If you remember previously when we talked about how reads were performed in a cluster and the fact that they have to go to the tablet leader, what follow reads allows you to do is read from one of the replicas in the raft group instead of the leader. What this can do is allow you to service reads, which may be actually closer to your customer, which can drastically reduce the latencies and improve the performance in a multi-region type deployment. But there is a cost associated with this. The cost here is that since you're now reading from a replica and not the leader of the data might not be that fresh. So while the latencies are reduced for reads, and consistency for these reads is not ASIC compliance. So it's up to you as the developer to decide if having the lower consistency is worth having the lower latencies and better performance for reads. The most unique deployment strategy that Yugabyte has compared to other databases out there is deploying two databases and then having them asynchronously sync data between them. In this architecture, you'd have two separate Yugabyte clusters that may be deployed in two separate regions, like say US East and US West. And each of those clusters could serve queries for the customers local to them. But then that data can be asynchronously sent to other clusters so that each cluster has 100% of the data. What this allows is for very low and highly performant queries for users regardless of which region they're close to. If a user were to be on the West Coast and then move to the East Coast, all their data would actually already be synced over there, and you wouldn't have to wait for the data to migrate over. That allows for very high performance local to that cluster. Now, again, there is a caveat here, and that is consistency. Since the data is getting asynchronously replicated across each cluster, there is a time when an insert could come in on the US West cluster, and it hasn't synced over the US East cluster yet. So if a read came in the US East at that time, the cluster may not have the data synced up, and the data may be stale. A current customer who is using this asynchronous replication is Kroger. Now, Kroger is a massive supermarket chain in the United States with thousands of supermarkets and department stores across the country, and recently has been investing heavily in growing their digital footprint with the onset of the COVID-19 outbreak. One of the major use cases they brought to Yugabyte is their shopping list service, where Yugabyte is used as a source of record for a majority of the United States and its millions of users. In this use case, where they use asynchronous replication is actually for a full backup of the database in case of a major outage. In this topology, they have their normal synchronous cluster, but then they have a second cluster which is being replicated to in case of a major problem. What they actually can do in this disaster scenario is switch traffic over to the consumer cluster and immediately start servicing reads and writes since all the data has already been synced to the cluster. This is what is commonly known as an active passive scenario that many RDBMS databases use now in order to achieve resilience. With Yugabyte, there's already this built-in resilience in a sync cluster, but with asynchronous replication, it gives you that extra little bit of a safety net. Another feature that Yugabyte offers is a read replica cluster. Most everyone is familiar with the idea of a read replica or read replica cluster, which is very useful when you want to have data closer to your users to speed up reads. These read replica clusters can drastically improve the performance for application reads, but at the cost, again, of consistency when reading from them. Since these replicas are not the tablet leaders for the data, when reading from them, there could be stale data. The speed at which it takes to update the replica cluster is about how long it takes to send data across the wire. This can be very useful when you need sub-millisecond reads and are not as concerned about having eventually consistent data. Now, Admiral is one customer who actually uses this. Now, they might not be the most well-known name, but the next time you go to a website with an ad blocker and it tells you to turn it off or pay up, that might actually be Admiral driving that with Yugabyte in the back end. This is one of Admiral's core offerings, and they came to Yugabyte because they needed high performance across the globe. All the major browsers like Safari, Firefox, and Chrome have added tracking protection or will phase out third-party cookies entirely. This fact alone is expected to drop ad revenue streams of some publishers by 50% unless it can figure out an alternative. What Admiral offers its customers is a way to bypass this and connect publishers and users directly. For Admiral, the speed of reads is critical. In order to get the millisecond latencies across globe, they utilize these read replica clusters. Here's how Admiral deployed Yugabyte for their application. As you can see in this topology, their it stretches across the globe in order to achieve the latency requirements in each region. So what they did is they have a single synchronous cluster that stretched across the US East, West, and Central. And then they have these two read replica clusters set up in Europe and in Asia. And what this allows them is that they are able to have this sub-millisecond read latency across the globe. They're actually able to get a below or close to 3 milliseconds for their reads. One new feature that I'm really excited about is geo-partitioning of data. Geo-partitioning is where you take tables or pieces of tables and pin them to a particular region. In this kind of setup, what you get is very low latencies for users local to the cluster, while also being able to keep the ACID level consistency for the queries, like a lot of our other options didn't have. An additional benefit is data residency. Since you could pin data to a particular region, this satisfies the data residency requirements like GDPR. The only downside for this type of deployment is that if there is ever a need to query data, say from Europe and you're in the US, you're guaranteed that that read or that write is going to take a long time since you pin the data in that particular EU region. There are two different ways geo-partition can be used with Yugabyte. The first way is by partitioning a table into a user-defined partitions and then pinning these partitions to the desired locations by figuring the metadata for each partition. So let's say we have a large imaginary bank called Yugabank, which wants to offer an online banking service to its users in many countries by processing their deposits, withdrawals, and transfers. They would require a number of features in order to properly serve their customers around the globe. The first would be high consistency and high availability. While Yugabyte automatically has it built into its architecture to be ACID compliance, we also need to have the geo redundancy, which again, Yugabyte offers. Next would be the high performance, which is where geo-partitioning actually starts to make an impact. In order to have a good customer experience, we would want the transactions to be processed in the lowest latency possible. If we were to use a standard RDBMS, say like Postgres, that would cause customers who are far away from the source to have extremely long latencies. But with geo-partitioning, we can pin data to the local Yugabyte region, allowing for better performance and end user experience. Another major feature would be for security and compliance. In Europe, for example, GDPR compliance requires all personal EU data to be stored in the EU. With geo-partitioning, we can pin the customer's data who lives in the EU to that local EU cluster and region to comply with these requirements. Again, the only caveat in this case would be that foreign transactions, there would be large latency since all the data is mandated to be stored in the EU. The second example of using geo-distribution is using duplicate indexes. Duplicate indexes are when there are multiple indexes on the same column within the same table. This is a great fit for when an index is read frequently across multiple regions, but maybe not updated on a regular basis. The reason for this is that if you have a copy of each index in each region, that means you can service reads with the index locally, drastically cutting down your read latencies. The downside is that for writes, which come into the index, you'd have to duplicate that write to each index while also having to incur the cross-region latency for each one of those writes. So an example where this could be a good fit is, say, for a car renting company with a website or app that allows you to lease a car of your choosing, which you can either pick up or get delivered from the office nearest to your location. Now, this could be a large company with thousands of offices spread across the US and handles multitudes of cars being leased every day. It would be important for the end user for their lookups on the types of cars you can rent to be as fast as possible. In the case of a multi-region deployment, to achieve that, you would want to serve the data locally. So in this case, it would be very beneficial to set up duplicate indexes so that all the data they need to look up on the cars is available locally, thus giving lower latencies to the customer. When we're talking about the cars that are available, you may not need to update the types of cars that are around. So again, this would be perfect for when you have a lot of reads, but not a lot of writes, and you want that data very quickly. Here's a diagram of all the different deployment strategies we went over today and the benefits of each strategy. So first, we have that multi-zone synchronous cluster, where you get that strong consistency, low read and write latency, as well as having that high tolerance. And it's mostly used for that kind of just zone level resilience where you're okay just having a single AZ go down and still being able to function. Then we have the multi-region stretch cluster. So with this, you had the consistency, which you can again tune with follow reads like we talked about, but in general, we have that very strong consistency. Now, for reads and writes, the problem starts becoming that you're going to have longer latencies overall because you're having to get acknowledgements from nodes that may not be within the same region. But the other good news is you have region level resilience now. So that means you can lose an entire region and still be able to function. Next is that cross-cluster async single direction. Now, I actually didn't talk about this, but with asynchronous replication, there's two different ways you can set it up. First is single direction, and then there's bidirection. In single direction, you still have that eventually consistent timeline for consistency, and you have that low read and write latencies. And you normally want to use that for like a backup or disaster recovery, this type of setup. The other option is bidirectional. And in this, that's where you have both clusters sending data across to each other. And again, you're going to have that eventual consistency. But then the good news is you'll have that low read and low write latency. This can be used for when you have, again, when you want to do backups or disaster recovery, or if you're not really too worried about the consistency of the data and just want to have that high performance. The next is read replica clusters. So you have that strong primary cluster is going to have that consistency, and it's going to be eventually consistent in those read replica clusters. The nice part here is you get the really low read latency, and the write latency could change depending on how you do your initial primary cluster. But in general, it would be pretty low, somewhere around 1 to 10 milliseconds. What's normally used for is when read latency is absolutely important and you're not as worried about the consistency. So if you need just fast, blazing fast reads, this is when you want to use that. The last, geo-partitioning. So you get that strong, you're back to that really strong consistency, that ACID compliance, but then you have that low read and write latency local to the data. But if you want to read data across from different regions, you're going to incur that really high latency for both the reads and the writes. And normally what we see this for is for compliances like GDPR. Thank you for joining me and talk about Yugabyte. All right, thank you for joining me and talking about how Yugabyte is able to be deployed in a multi-region setup that allows for resilience, high performance, and achieve your day-to-day residency requirements. If you have any questions, let me know, and please join our community Slack using the link here. Enjoy the rest of the conference.